This is the solutions for calculus homework number 20 from the textbook. So this is on page 43 and 44, the following problem numbers. So we have four functions, all that give populations in a town in terms of time, t, in years. So A is asking which has the largest percent growth rate and what is that growth rate? So taking a look at all four of these, the percent growth rate comes from, if we look at our original form for this function, we're actually looking at the base, which is A in this case, because A is equal to 1 plus the rate, which is the growth rate we're talking about here. So looking at all of these, I have 1, 2, 3, and 4 as our little numerals here. And so the growth rate for I is going to be 1.12 minus 1, or 0.12, or 12% growth rate, because A is greater than 1. So if A is greater than 1, that's growth. So for 2, we would have 1.03 minus 1, which is 0.03, or 3% growth. We have, for a third, 1.08 minus 1, which is 0.08, which is 8% growth. And then for the last one, we have 1 minus 0.9. I'm sorry, I did this backwards. We have 0.9 minus 1, my fault, which is negative 0.1, or 10%, and it's not growth, it is decline in this case. So, which has the largest percent growth rate? Well, that would be number 1, which has a growth rate of 12% per year. So for B, which town has the largest initial population? Well, this comes from the other part of our thing here. We're looking at F naught, which is the initial value. So for 1, we have an F naught of 600, so initial population of 600. For 2, we have an initial population of 1,000. For 3, we have an initial population of 200. And for 4, we have an initial population of 900. So which has the largest initial population? That would be 2, town 2, and that population is 1,000. Then for C, we're asking which is decreasing in size. Which ones? Well, this would be 4, because we see that it is the only one that has a negative growth rate, and that rate is negative 10% per year. Number 3 asks us to look at graphs and see which of these are increasing at certain rates and kind of match those descriptions to these numerals. So for A, we want to see a population that increases at 5% per year compared to a population that increases at 8% a year, compared to one that increases by a static 5,000 per year, and compared to one that is stable. So let's actually do several of these at the same time, because going in order is not always the best choice. So I'll actually start with D because it's the most simple. Line V, Roman numeral V here, is a flat horizontal line, so the population does not change. That is what it means by stable. For a line that increases by 5,000 per year, now we're looking for a linear function. So the only one here that is linear and increasing is Roman numeral 3. Now if we're looking at two different increases, we have one that increases at 5% per year and one that increases at 8% a year. The one that increases faster must be I. See how it is having a steeper slope than Roman numeral 2. So the 8% must be Roman numeral 1, while Roman numeral 2 is increasing at only 5% per year. So simply a case of knowing linear versus exponential growth. Question 5 asks us to look at some GDP here. So we're trying to find a formula for G in billions. We know that in 2007, so this is years after 2007, we want to give a formula where it increases by 3% per year. So let's go through this one step at a time. So the first part is we're going to find A, our base, because we're trying to get to a form of f of x, which is equal to our initial value times A, which is some base, to the x. So A is 1 plus the rate. Well, our rate is 3% per year, which we should write as 0.03 is a decimal. So A is going to be 1 plus this 0.03. So for us, this base will be 1.03. Then our f naught, our initial value, is the g in the initial year. So in 2007, g was $310 billion. So if we want to write this formula, so it's g in terms of t, because it's given that we want to do this in t years, we'll have our initial value, 310, times our base, which is 1.03, raised to the t. And this is our exponential growth function. For b, we just want to increase it by $8 billion per year. So for this equation, we're just going to use slope-intercept form. So we're increasing by $8 billion per year, and we're starting at $310 billion. And that's all there is to 5. Question 8 takes a look at an exponential growth function for population for the entire world. So just dissecting this formula, which I'm going to rewrite, we have p equals 6.4 times 1.0126 raised to the t. So just pulling out initial values here, we have this, which is our initial population. So I'm going to say that's p0, which is 6.4, and that's billion people. And then we have this, which is our a, which is 1.0126. And now we have all the information we need in order to figure this out. So since a is equal to 1 plus r, we can say that r will be equal to a minus 1. So in this case, we'll have 1.0126 minus 1, or 0.0126, which we can rewrite as a percentage, just multiply by 100, so 1.26%. And so this is our yearly percent growth rate for the world population. Now for B, we want to know what the world population was in 2004. So this starts in 2004, so that's just our initial value. So our initial value is going to be 6.4 billion people. Then, what does it predict for the world population in 2010? So this is number of years since 2004. So from 2004 to 2010, we are going to have 6 years pass. So t will be equal to 6. So we'll simply plug in for our population function. We'll have 6.4 times 1.0126 raised to the 6th power. So in this year, we will have a population of 6.9 billion people. Now for C, we want to find the average rate of change between these 2 years. So our average rate of change is going to be our final, or our second population, minus our initial, over our 2 years, or our time period. So for us, that's going to be 6.9 billion minus 6.4 billion, which was our initial, over our change in years, which is 2010 minus 2004. So this really just works out to be 0.5 divided by 6, which you can do easily in your calculator, and works out to be an average rate of 0.083, and that's repeating, billion people per year. So if you're worried about the interpretation of this, pay attention to the units. Our numerator is going to be billions of people, and our denominator is going to be years. So for this one, we're looking at the rate at which quinine leaves the body after a dose. So quinine is used to treat malaria, so this is a very important aspect of drug understanding. So we have a 50 milligram dose. Now we're finding the formula for the amount, which is A. So our initial amount, A0 or A0, is going to be 50 milligrams. Then we know that it leaves the body at a rate of 6% per hour. So our rate is going to be negative 6%, or in decimal form, negative 0.06. So A will end up being 1 plus R, which is 1 minus 0.06, or, when we put this together, 0.94. So to write our equation, A as a function of time, we'll have our A0, which is 50, times our base, which is 0.94, raised to the T, which is hours after injection. Now B asks how much quinine is left after 24 hours. So we'll just find the value for this function at time of 24. So we have 50 times 0.94 raised to the 24th power. So how much quinine will be left? Take this to your calculator. You should have 11.325 milligrams left in your body. Now C says graph A as a function of T. So you can do this in as much detail as you want. I'm just going to do the quick version and show you what this looks like. So we have A, which is amount, on the vertical, and we have T on the horizontal, and we're going to start at 50 milligrams. Then it will look something like this, where it slowly changes our slope so that the slope is shallower and shallower over. For number 10, we're going to be looking at sales as a function of time that increases at a continuous rate of 4.3% per year. So, looking at part A, we want to write our sales function, S of t, and in order to do that, we need to know, since this is an exponential growth, because we have a percentage growth here, we have an initial sales of $5.1 billion. So let's just write that as 5.1. And then we want to figure out our base, which is A, and the problem here is we need our rate first. So our rate is 4.3% increasing. So we'll rewrite that as 0.043. So A will be 1 plus this, so 1 plus 0.043, leaving us with a base of 1.043. So our S of t function will be 5.1 times 1.043 raised to the t. Now B asks for the annual net sales in 2015. So we will look at this in terms of what t is defined as. So for t, we have years since 2008. So in order to find the sales in 2015, we need to figure out how many years have passed. So we have 2015 minus 2008 gives us 7. So this is our t. We want to find when the value of s when t is 7. So taking our function and substituting 7 for our time, we have 5.1 times 1.043 raised to the 7th power. And this, once we take it into a calculator, gives us 6.85, we'll say, rounded. And that's going to be in billions of dollars. So we'll just write billions of dollars. Now, C says, use a graph or trial and error to estimate the year in which annual net sales are expected to pass $8 billion. So, just going through trial and error with my calculator, I came up with a value of about 11 years for T. So about 11 years. Now, this is asking us what year does it actually occur. So this is since 2008. So we want to estimate somewhere in the year 2019. as a good estimate for when sales actually pass $8 billion. So Consumer Price Index is basically the purchasing power measure for the general public. In 2009, the CPI was 211. So we want to write a formula for CPI as a function of T in years after 2009, assuming that it increases by 2.8% every year. So we'll go ahead and say that this is CPI as a function of T. And in order to write this, we have our initial value, CPI 0, in 2009 is 211. We also have a growth rate. So our rate is 2.8%, which as a decimal is 0.028. So our factor by which we grow will be 1 plus r, which is 1 plus 0.028. So our factor here is 1.028. So our CPI will end up being a function of 211 times 1.028 raised to the t power. For question 15, we're actually given a set of data and we want to find a possible formula for the function represented by this data. So what we're going to do is we're going to look at relative change from year to year in order to come up with an exponential function. So our relative change, in case you've forgotten, is going to be change in y over y. So for the first 2 years, or for the first 2 data points, we're going to have 6.02 minus 4.3 all over 4.3. So this relative change, if we plug this into a calculator, is going to be about 0.4. And we're going to keep doing this. So so this is 0 to 1. Now we'll do 1 to 2. And we'll have 8.43 minus 6.02 over 6.02. And so what we're doing by doing this is we're actually coming up with the rate at which these are growing. So we get, again, 0.4. And at this point, it's probably pretty safe to assume that it's increasing by a relative rate of 0.4 per year. So that means that R is equal to 0.4, right? Because if you look at this, it's increasing by about 40% per step. So there's our R. Now what this means for us is that we now have an A, because A is 1 plus R, or in this case 1 plus 0.4, which just gives us 1.4. Now the next bit is we just need our initial value, right? Our F naught in this case is going to be 4.3. So we can write our f of x as an exponential function where we have 4.3, our initial value, times 1.4 raised to the x.